Based on what we did in class today, we started kind of looking at trends on the periodic table. We looked at size today. There's several trends we're going to look at, but I'm just going to talk for a few minutes and not really write anything down. But basically, the physical and chemical properties of elements and their compounds are dependent upon the outermost or valence electron configurations. When the elements are arranged in the periodic table in order of ascending atomic number, which is how we have our periodic table set up, a regular change in the outermost electronic configurations is observed. In turn, a regular variation of properties is also observed. This is called the periodic law or periodicity. As a period is traversed, or as you go from left to right across a period, which is a row, certain regular, repeatable patterns can be observed, which lead to the ability to make predictions about unknown properties of elements and their compounds. Additionally, elements that are in the same group, so a column, have similar outer electron configurations, and often behave in similar manners to one another. These two facts, how stuff corresponds left to right across a period or up or down in a family, led to the observation of gradual changes in the physical and chemical properties of elements and their compounds when moving about the periodic table. In order to illustrate these changes, we will consider a number of periodic trends and patterns observable in the periodic table. While these mostly hold true, I have to note that there's several exceptions, which just happen, which aren't really all that explainable, other than there's exceptions to pretty much every rule in science. We're going to set this up basically like an outline. So we're just going to start with Roman numeral 1. And we're going to talk real quickly history of periodic table. And I'm going to make my ink a little bit more narrow. Okay, so history of periodic table. Kind of two names you need to be familiar with. The first one is Mendeleev. His first name was Dmitri, and he was a Russian scientist. His time frame was about 1869. And he basically saw that there were these trends in elements, that alkali metals reacted with water, they turned water basic. They figured there must be something about them that made them similar. We now know that's the outer electron configuration. The alkali metals always ended in S1, but he kind of arranged these and found that if he arranged them based on atomic masses, we might just call these molar masses, but based on atomic masses, so it's basically just molar masses with the unit AMU instead of gram. But he based on atomic masses and found that, for the most part, his periodic table held true. All right, and there were periodic trends. That's the periodic table. That things held true as columns changed, as periods changed. The other guy is Henry Moseley. And Moseley was around the beginning of the 20th century, I think 1917 or so. The great thing with Moseley is, by this time we had discovered protons, electrons, and neutrons. Mendeleev's time was 50 years earlier. We didn't know about those things. So Moseley made a couple changes to what Mendeleev had done, and he based his periodic table on atomic numbers. All right, and that is how they are still based. Right, and as the atomic number goes up, we add a new element on the periodic table. All right. The next thing we're going to look at, just real quickly, is just a return to our Unit 3 stuff, which was electron configurations. So, electron configs and periodic table. And just a couple things here. Groups and families. Alright, these are columns on the periodic table. Woo. So groups and families. There's 18 of them. And it's just numbered 1 through 18 across the top of the periodic table. Those F block at the very bottom do not have a family number. But all the elements in groups and families have same or identical what are we going to call them? Valence electron configurations, or just those outermost electrons are identical. Valence electron configs. Alright, and B, we might just call these periods. And on our periodic table, there are 7, although we can postulate more of them. But there's 7. And all elements in periods have the same highest energy level, because that is really what our N tells us. Highest E level. And that's really all you need to know about electron configurations of the periodic table. So the periodic table is periodic. Alright, there's periods that happen periodically because we have these groups, and in our groups we have same valence electron configurations, and as we end over here on P6 at the end of the periodic table and start a new row, our new row, everything has the same energy level. Alright, so we're going to start looking at some trends. We're going to look at the trend we looked at in class today, which was size. We're also going to look at ionic size. So we're going to look at 2 sizes right now, and that is going to be it for your podcast tonight. So we're going to do periodic trends. And our first trend is going to be atomic radius. Or because we're going to talk about a lot of them, we're just going to call it atomic radii. Alright, and what is atomic radii? It is defined as half of the distance between two bonded atoms of the same element. 2 bonded atoms of the same element. So for instance, if we had 2 oxygens, so here is our oxygen proton, here's another oxygen proton, and then here's the shell of electrons, there's the shell of electrons. This distance, so we have distance from proton, or from nucleus to nucleus. Alright, so half of that distance is what we would say is the radius of our atom. So that right there, radius, is our size. So we're talking about size. And we're going to look at 2 trends. First trend is going to be the group trend. So group is in a column. But our group trend is essentially, from top to bottom, they increase. Increase from top to bottom. From top, we're just going to say top down. Alright, and basically 2 reasons for that. First reason is, as we go from top to bottom, we have higher energy levels and if we think back to quantum numbers, what does N tell us? N is our energy level, and it tells us distance from nucleus. So really, higher energy levels equal larger orbitals, because we are getting further from the nucleus. And then our second kind of reason is, and this is really where you get into, in AP Chemistry, if you can name drop and use specific terminology, you're more likely to kind of get answers, you're more likely to get points, especially on the free response portion. However, you can't just put a name drop, you can't just say effective nuclear charge and not know what you're talking about. Okay? So the other reason is was embedded within the ChemQuest thing you did in class today. But there is more shielding, and I think I kind of talked about shielding within your ChemQuest. More shielding by inner shell electrons. By inner shell electrons, or inner energy level electrons, but inner shell electrons. So what does that mean? That is equal to saying, alright, I'm going to scroll this down again. So that is kind of the same as saying we have reduced the effective, and this is the name dropping thing, the effective nuclear charge. An effective nuclear charge is typically, if you look in your book, it is Z is the effective nuclear charge, and just EFF is effective. But Z is our nuclear charge. And ZEF can be calculated like this. ZEF equals the Z actual, so the actual nuclear charge, minus electron shielding. And your ChemQuest today in class did a great job of saying, so if we are talking about fluorine, which has 9 protons, plus 9, our first energy level is going to be 1s1, 1s2. Second energy is going to be 2s1, 2s2, and then we're going to have 2p1, 2p2, 2p3, 2p4, 2p5, and that's our 9 electrons. So these electrons in the second energy shell, what do they feel? Do they feel a plus 9 pull on them? They don't, because these 2 electrons are basically shielding part of this plus 9. So because there's 2 electrons, it's going to shield 2 of those plus 9s. So really, this outer energy level feels a plus 7, pulling it towards the nucleus. Alright, and that is effective nuclear charge, and just the concept of shielding. So what these outermost electrons feel compared to what they could be feeling. So actual charge versus effective nuclear charge. Our other trend is going to be based on, let me get my color back, is going to be period trends. And period trends, and again, you had this in your notes today, but period trends can be somewhat confusing the first time, period trends. And again, we're going to basically look at, as we go across a period, we are adding more protons to nucleus. How come? Because as we go across a period, atomic charge, or atomic number, is changing. So more protons in nucleus as we go from left to right. So, what does that mean in terms of effective nuclear charge? Alright, because we're adding more protons to the same place, the nucleus, and as we go across a period, where are we adding everything? We're adding everything to the same energy level. So because this energy level is the same distance from the nucleus, if we keep on making this a bigger value, so we're kind of making the magnet, the positive pull of our magnet, larger and larger, what does that do to the pull? It increases the pull. Okay? So more protons and neutrons means there's a greater effective nuclear charge. So greater ZEF. And greater effective nuclear charge means there's a greater pull. If we have a greater pull, that equals smaller radius. Or smaller radii. Alright, up here I probably should have done this, a reduced effective nuclear charge. So because it doesn't feel as much, we're going to have larger radii. But again, the idea of effective nuclear charge is a great term to use when answering AP questions. And then the last thing we're going to look at today is ionic radii. Okay, so what happens when we turn elements, or just atoms, into ions? So, kind of quick review, we might just say cations. Okay, so cations are typically metals. Okay, how does something become a cation, or what is a cation? Cations are positive charge. And why does something have a positive charge? Positive charge equals a loss of electron. Alright, so if we think of this in terms of, if we have something like sodium. Alright, so sodium is atomic number 11. So typically it has 11 protons attracting 11 electrons. However, when it becomes sodium ion, okay, how many protons do we have? We still have 11 protons. But how many electrons is this attracting? Well, it's attracting 10 electrons. And not only is it attracting fewer electrons, but what electron was lost here? The electron that was lost was a 3s1 electron. Which means what electrons do we have left? Well, we have 2s and p electrons. So we've not only basically gotten rid of this third energy level, which we could have way out here, okay? So that 3s1 is now gone. We've reduced it back to our second energy level. But another way to look at it is we have 11 protons attracting only 10 electrons. So all that to say is cations are smaller compared to atom. So cations are smaller compared to atom. So the last thing we're looking at is anions. And kind of just like our last definition, anions are typically nonmetals. And they have a negative charge. Negative charge from gaining electrons. Alright, so if we look at something like chlorine. So chlorine has 17 protons, and it has 17 electrons. Alright, but when we talk about chloride, so because I'm changing my ending to ide, I'm implying it has a charge. It still has 17 protons, but now it has 18 electrons. So in this case, what happens is we have 17 protons that are typically attracting 17 electrons to themselves. But now once we've added another electron, can 17 protons just as effectively attract 18 electrons? And the answer is no. So our size gets larger. Another reason our size gets larger, if we have 18 electrons instead of just 17 in our electron cloud, what do electrons do in relation to each other? Because they're both negatively charged, they repel each other, which again kind of puffs up our cloud because we just have more negative charge, and more negative charge repelling each other makes for a bigger atom. So the trend here is that anions are larger than the atom. And that is it. So main things to take away is the ionic radii differences and effective nuclear charge. If you can do that and use that effectively on AP tests or on a test in my class, it'll make you look smart. And if you look smart, I've heard the graders are more likely to give you the benefit of the doubt if there's a question on another part of your test just that you look smart in one part and it makes you look smart overall. So I will see you in class tomorrow. That is it.